Hi, my name is Hana Warner, and today we'll be talking with you about the design and implementation of a PID controller for interferometer stabilization. So a proportional integral derivative, or PID controller, is a feedback loop used to stabilize stochastic systems. They're frequently used in instrument and industrial control and for automated control systems, such as in your heating and cooling systems, your cruise control in your car, motor controls in robotics, or pressure controls, and they're favored because they stabilize quickly and hold for long periods of time and are adaptive linear controllers, so they'll respond to any changes to set point or fluctuations in your system's environment. So the proportional term corrects purely based on the current error signal, where the integral term looks at all the error signals to prevent any steady state error, and the derivative slows the response by preventing overshoot based on the rate of change in your error. We're using the PID loop to stabilize a megacent interferometer in this project. Stability is really important in interferometric systems because they're so sensitive and the wavelength of light is so small, so any fluctuations in environmental temperature can yield large changes in interference. Ultimately, we're trying to stabilize our system for a long-term single and two-photon experiment, so these will run for several hours. Currently, fluctuations in our system's environment and some temperature stability issues in our lab are making this long-term data collection very difficult. And in particular, with our loop, we're looking at a displacement power relationship. So this way we can check our power difference on a laser, and this has the benefit of requiring less equipment, so hopefully there will be a faster response time. However, we did have to modify our control system a little bit to adapt to this nonlinear relationship, which I'll get into in a couple of slides. So this is our experimental setup. In this particular project, we were looking at single photon interference, but this is similar to the setup that we'll use for our long-term data collection experiments. So each interferometer in our system is equipped with a mirror mounted on a piezoelectric controller, a PZT. In our first interferometer, this mirror is just scanned across the 3.5 micrometer range of our PZT so that we can see our constructive and destructive interference. And our second interferometer actually houses our PID, and so that the displacement of that mirror will be adjusted based on our power output of our probe laser compared to whatever we want our set point to be. Ultimately, we are looking into replacing our scanning mirror with a PID loop, and we're running our long-term experiments, so these will run in parallel for our long-term stability. This is our modified PID design. As you can see, our error signal is computed relative to the range of our laser's powers. This is for a couple reasons. We're working at a very low power laser. It's about 30 microwatts. So we had a really slow response time without this relative computation. We also wanted to make sure that we were able to keep these coefficients lower. Our I term in particular, which stabilizes at a non-zero point, would have large fluctuations when we had strong vibrations in our system, so that would result in a huge offset. Also, we wanted to be able to keep these coefficients uniform as we changed the laser's power. We also introduced a bias that scan before we entered our PID loop to increase our response time and again keep these coefficients a little bit lower. And so that would scan the PID mirror to a position that was within plus or minus 5 microwatts of our set point before we entered our loop. We also checked to see whether or not the laser, our output power was increasing or decreasing with changes in position, so that we knew a little bit more about our system and knew what phase we were at, which would also be beneficial for future experiments that we run. So our PID was processed in a C++VL interface through LabVIEW. So we ran a couple simulations to approximate our coefficients and see how our PID was responding. The piezoelectric controllers had 2 degrees of motion, so that's why we looked at 1 and 2 degrees of error. And so running the PID with our system, we saw that we were able to correct for that long-term power drift that we were seeing without the control loop. And we're reasonably stable around our set point. We were usually within about 5% error. So running it with our single photon interference, we saw that we applied 0 to 75 volts to the crystal for so that we could, in 2-volt increments, so that we could scan across that 3.5 micrometer range, as I stated prior. We saw that the PID had a much smoother scan. And without the PID, we didn't hit all 37 steps that we were looking at, or you can't see them all individually. I think that's because of the drift in the laser or just fluctuations that resulted in not getting to everywhere that we wanted it to go. However, we did also experience a power drift in our laser when we were looking at these scan without the PID, which you can kind of see the phase shift here. Also, we had a lower visibility while we were running the PID loop. You can see here that our constructive interference with the PID was around 3,100 photons compared to almost 4,000 without the PID. And our without the PID, our destructive interference is a little bit closer to 0 than with it. But again, we think that this is primarily due to our laser drift and our step size when we were scanning our mirror. Because we fit that nice tiny little relationship that we were expecting both with the position power and the photon count voltage. We were looking at those relationships, and they're not as apparent without the PID. So that's indicative of the problems due primarily to the power drift. We were stable around about 25 megawatts with the PID and only at about 19 megawatts without it. So we were reasonably successful in stabilizing our interferometer around a set point. We corrected for that long-term drift in our laser, and we were usually within about plus or minus 2 to 4% of our set point relative to the range. However, our stability still fluctuated a lot with changes in our environment. We had a lot of temperature control issues in our lab. So usually Monday mornings before everything kicked on, we could get pretty good stability within about 1 or 2%, but as the day went on, the stability got worse to 4 or 5%. So some improvements we're looking to make are to implement a low-pass filter in our system. Our interface is pretty slow. We're only able to run our loop about every 50 milliseconds, so we want to try to eliminate some of that high-frequency noise. We also want to look into phase-based corrections instead of power-based corrections because that is a linear relationship and may correspond better with our linear controller. And we'll apply this control to our system to run our long-term experiments. So thank you so much to these people, and thank you for listening.